Hello everyone, welcome back to our maths class. We are discussing the chapter real numbers, right? And the last class we have discussed how to prove root 2 is irrational, root 3 is irrational, how to prove 3 root 2 is irrational, etc. Today we are going to discuss a new topic, that is rational numbers and their decimal expansions. Rational numbers and their decimal expansions. So let's discuss this topic in detail. Okay, dear students, let's revise which we have discussed, which we have learned from 9th standard. Rational numbers and irrational numbers. Rational numbers, decimal expansion of rational numbers are two types. Terminating decimal expansion and non-terminating repeating. Non-terminating repeating. Repeating means recurring. Okay. So, for a rational number, two types of decimal expansion can happen. Terminating and non-terminating repeating. Okay. For example, terminating means, yes, terminated, 0.375. It's over. Okay. Then 0.3, 0.75, etc. Okay. Non-terminating, that means endless. Okay. Repeating. Endless plus repeating. Okay. Repeating means recurring. Okay. 0.321, 321, 321. It's not ending. Okay. So, non-terminating but repeating. Here, 3 digits are repeating. 321, 321, 321. Okay. Here also 0.52, 52, 52. 2 digits are repeating and it's not ending. That is non-terminating. Okay. So, for a rational number, decimal expansion of a rational number can have two types, terminating decimal expansion and non-terminating repeating or non-terminating recurring decimal expansion. Okay. For irrational numbers, non-terminating, non-recurring. That means endless but not repeating. Okay. Different digits are coming. 0.10, 100, 10, like that. We cannot predict which number will come next. Okay, like that. Not repeating, non-terminating. Okay. In this class, we are going to learn about rational numbers and their decimal expansion. That means rational numbers and their decimal expansion. Okay. Okay, dear children. Here I wrote 3 rational numbers having terminating decimal expansion. 0.375, 0.104, 0.0875. Okay. So, this is rational number. So, we can express this rational number in the form P by Q. How to express this rational number in the form P by Q? Yes, 375 by 1000. 1000. Clear? So, P by Q form. Or 375 by 10 cube. Here, how to express 104 divided by 1000. That is 104 divided by, here also 10 cube. Here 875 divided by 10,000. Why 10,000? Yes, after decimal 4 digits are there. Okay, here 875 divided by 10 raised to 4. Okay, while checking the denominators, we can see that all the denominators are powers of 10. Clear? Okay, next 375 by 10 cube. How to write 10? 2 into 5. 2 into 5 cube. Or 375 divided by 2 cube into 5 cube. 2 cube into 5 cube. Okay. Next, in numerator also we need to factorize this numerator. Okay, how to factorize? 375, just factorize using 5, 37, 3, sorry, 5, 7 times in 25, 5 times, again 5, 1, 5, again 5, 3. That is 5, 5, 5, 5 cube into 3 divided by 2 cube into 5 cube. Okay, in numerator and denominator 5 cube is common. So we should cancel all the common terms, common factors in numerator and denominator. Then what remains here? 3 by 2 cube. 3 by 2 cube. In numerator 3, denominator 2 cube. Now 3 and 2 cube means 8. 8. 2 into 2 into 2, 8. Now 3 and 8 are co-primes. No common factors. Okay, only one as common factors for 3 and 8. Clear? The next 104 by 10 cube. 104, how to factorize? 104, 2 in 10, 5 times, 52, again 2, 2, 6, again 2, 13. So 104, 2 cube into 13. 2 into 2 into 2. Okay. By 10 cube, how to factorize? 2 cube into 5 cube. Okay. Well, in numerator and denominator, 2 cube is common, so we cancel them. Then 13 by 5 cube. Okay. Then 875. 875 factorize using 5 in 8, 1, 37, 7 times, then 25, 5, again 5 in 17, 3 times, then 25, 5 times, again 5, then 7 times. Okay, so 5 into 5 into 5, 5 cube into 7 divided by here 2 raised to 4 into 5 raised to 4. Okay, then here 5 cube and here 5 raised to 4. So 5 cube we can cancel. 5 into 5 into 5, 5 into 5 into 5. We can cancel. Then what remains in numerator? 7. In denominator 2 raised to 4 into 5 raised to 1 or 5. Okay. Okay, dear students. So 0.375 is a rational number and which is also terminating decimal expansion, and we express this in the form p by q. P by q, and we cancelled all the common factors and we got co-prime numbers, numerator 3 and denominator 2 cube. Okay, here 0.104 we got, this is also a rational number, and it has a terminating decimal expansion, and we expressed this in the form p by q. Okay, numerator and denominator are co-primes now. 13 and 5 cube are co-primes. 0.087 also a rational number, and it has a terminating decimal expansion, and we expressed this rational number also in the form p by q, where p and q are now co-primes. Okay, then check these denominators. See, check these denominators. Here 2 cube, here 5 cube, here 2 raised to 4 into 5 raised to 2. Okay, we see all these denominators or q. Okay, q's are in the form 2, 2 or 5 terms. Okay, 2 here 2 cube, here 5 cube, here 2 raised to 4 into 5, 5 raised to 1. Okay. Okay, next we have to discuss, using these results we have to discuss our first theorem. Okay, dear students, this is the theorem. Okay, let x be a rational number. X be 0.375 is a rational number. Suppose, okay, x be a rational number whose decimal expansion terminates. Decimal expansion terminates. Then x can be expressed in the form p by q. This is a rational number terminating. Okay, x, then it's x, then this rational number can be expressed in the form p by q, where p and q are co-primes. 3 and 8 are co-primes here. Okay, and the prime factorization of q is of the form, prime factorizations of q is of the form, that means denominator p, here p, q is 2 cube, here 5 cube, Here 2 raised to 4 into 5 raised to 1. Okay, this prime factorization of denominators is of the form 2 raised to n into 5 raised to m, where n, m are non-negative numbers. Okay, this denominators or factorization of q should be in the form either 2 raised to m. Here p is what is the form of q? 2 raised to n. Here 5 raised to, here q is 5 raised to m. Here 2 raised to n into 5 raised to m. Okay, so if x is a rational number and it has a terminating decimal expansion and it can be expressed in the form p by q, where p and q are co-primes, then factorization of q should be in the form either 2 raised to n or 5 raised to m, or both 2 raised to n into 5 raised to m. Okay, this is our first theorem. Okay, dear children, we discussed our first theorem. This is our second theorem. Let x equal to p by q be a rational number. X equal to p by q. For example, x is equal to 3 by 2 cube or 3 by 8. 3 by 8. Okay, 3 by 8 or 3 by 2 cube. X equal to a rational number p by q. Okay, such that the prime factorization of q is of the form 2 raised to n into 5 raised to m, where n and m are non-negative integers. Here prime factorization of q is of the form 2 raised to n. Okay, then x has a decimal expansion which terminates. Then this x, this rational number, have a decimal expansion. That means this decimal rational number have a terminating decimal expansion will have. Okay, that means how to write this? Yes, here 2 cube into 5 cube. Here also 3 into, just add 3, 5 cube. That is 375 by here 10 cube. That is 375 by 1000. That is 0.375. Clear? Just converse of first theorem. Okay, x equal to 3 by 8 is a x equal to p by q be a rational number. X equal to 3 by 8 is a rational number, and prime factorization of q. Prime factorization of q is 2 cube is of the form 2 raised to n. Then this rational number will have a terminating decimal expansion. Clear? So, if we know this theorem, no need of this type of calculations. Okay, if 3 and 3 by 8 or 3 by 2 cube is a rational number, then 3 and 2 cube are prime numbers, co-primes, p and q are primes, then we can say that this rational number has a terminating decimal expansion. Okay, no need of calculations. Clear? So let's go to our third theorem. Okay, dear children, this is our third theorem. Let x equal to p by q be a rational number. P by x is a rational number such that the prime factorization of q is not of the form 2 raised to n into 5 raised to m. Prime factorization of q is not of the form 2 raised to n into 5 raised to m, where n, m are non-negative integers. Then x has a decimal expansion which is non-terminating, repeating, recurring. Clear? If, see, 3 by 2 cube 4 or 13 by 5 cube, okay, 7 by 2 raised to 4 into 5, okay, all these are rational numbers having q as the prime factorization of q of the form 2 raised to n, 5 raised to m, 2 raised to n into 5 raised to m. If this type of rational numbers have terminating decimal expansion. Okay, if p by if x is a rational number, p by q is a rational number, then factorization of q is not of the form like 3 by 7. 3 by 7. 3 by 7 is another rational number, but here factorization of q is not of the form 2, okay, 2 powers of not here 7, not 2 or 5. Okay, so this type of um, rational number have such kind of decimal expansion, non-terminating repeating, okay, non-terminating repeating decimal expansion. Clear? So this is the third theorem. Okay, so dear students, we have discussed rational numbers and their decimal expansions. Okay, so we have discussed 3 types of theorems in this class. So I hope you all have enjoyed today's class.